Welcome to This Explainer. Today, we're doing a deep dive into something that literally runs the world. We want to equip you, as policymakers, with a foundational understanding of hydrocarbon chemistry. Our goal is to give you the objective, structured data you need to really weigh the immense energy benefits of these compounds against the profound environmental costs.
So, let's kick things off with a pretty wild question. How on earth do combinations of just two simple elements manage to power the entire globe while at the exact same time posing a massive threat to our climate? We are, of course, talking about hydrocarbons, the compounds that essentially drive our modern industrial world.
Here is our roadmap for today. We'll be moving from the micro to the macro. We'll cover 1. The chemistry of hydrocarbons. 2. Structures, isomers, and models. 3. Fuels, solvents, and plastics. 4. Environmental impacts, specifically comparing coal versus LPG. And finally, 5. The future of energy, looking at methane hydrates. Okay, let's jump right into section 1, the chemistry of hydrocarbons. We're starting at the microscopic scale to demystify exactly what these incredibly powerful molecules actually are. Now, hydrocarbons are, well, exactly what they sound like. Organic compounds made entirely of carbon and hydrogen. That's it, just two elements. Found deep underground, these resources originally came from the anaerobic decomposition of ancient, buried organisms over millions of years. Today, we extract these simple combinations of carbon and hydrogen as fossil fuels, and they absolutely dictate our global energy economy. So how do we classify them? It basically boils down to 3 main types based on their atomic bonds. And honestly, the names totally give away the structure. First up, we've got saturated hydrocarbons, like alkanes ending in -ane. Think methane. These are basically open chains with only single carbon-to-carbon bonds, completely saturated with hydrogen. Next are unsaturated hydrocarbons. These have double bonds, those are your alkenes ending in -ene, or triple bonds, which are alkynes ending in -ine. And finally, we have aromatic hydrocarbons. These are a special type that form closed ring structures, kind of like benzene. Moving on to section 2, structures, isomers, and models. Let's look at how these atoms actually bond together and how chemists visualize their invisible architecture. To intuitively grasp these structures, chemists love using simple physical analogies. Think back to grade school science. You can use little plasticine balls to represent the carbon and hydrogen atoms. Since carbon always forms 4 bonds and hydrogen just 1, they snap together in very specific ways. For those saturated alkanes we just talked about, you do straight, rigid toothpicks to show stable single bonds. But for the unsaturated alkenes and alkynes, you'd use flexible springs. And that's because those springs perfectly represent the actual chemical tension built into those multiple bonds, which ultimately dictates how volatile and energy-dense a fuel is going to be. Now, a huge part of mapping this microscopic architecture is identifying the carbon atoms based on what they're attached to. A primary carbon is attached to just 1 other carbon. A secondary is hooked to 2, a tertiary to 3, and a quaternary, sometimes called a neocarbon, is connected to 4 others. And as policymakers, understanding this geometry isn't just trivia. This structure completely dictates how these molecules react, which directly impacts the safety, storage, and refining regulations that cross your desks. This brings us to a seriously fascinating concept, isomerism. Basically, isomers are molecules that have the exact same chemical formula, meaning the exact same number of carbon and hydrogen atoms, but they are arranged completely differently. Because the physical structure is different, they act as entirely distinct chemical substances. They can even have completely different physical properties, like different boiling points. It's like having the same set of Lego bricks, but building a spaceship instead of a car. Take a look at this. A single chemical formula can branch out in so many ways. Let's look at pentane, an alkane with 5 carbons and 12 hydrogens. You can arrange those exact same atoms in a continuous, straight chain, or they can form branched chains. These chain isomers prove that the physical shape of a molecule is just as critical as its chemical formula when determining how it's going to behave in the real world. All right, that scales us up beautifully to section 3, fuels, solvents, and plastics. Let's explore how these chemical properties are harnessed for human progress and manufacturing. You probably don't look at a barrel of crude oil and immediately think of your smartphone case, right? But modern plastics are a direct result of this hydrocarbon chemistry. At a refinery, crude oil gets distilled and separated into lighter groups called fractions. One super important fraction extracted is called naphtha. Through chemical processes like polymerization or polycondensation, the simple molecules in naphtha get linked together into long polymer chains. And boom, that is how we get the plastics we rely on every single day. And it's not just heavy industry and power plants. Certain hydrocarbon gas liquids, things like propane, butane, and ethane, are absolutely essential raw materials for household items. I mean, hydrocarbons give us our cooking and heating fuels like LPG and natural gas. There are petrol and diesel. They're the base solvents for the paint on our walls. They even make up the foundational building blocks for synthetic fibers like nylon and polyester in our clothes, not to mention the lubricating oils and waxes that keep all our machines running. So let's zoom out even further. Section 4, environmental impacts, specifically comparing coal versus LPG. As policymakers, it's vital to impartially analyze the global footprints and trade-offs of these fuels. To truly grasp the economic scale we're dealing with here, just look at this number. The net income of the global oil and gas industry hit a record $4 trillion in the year 2022. $4 trillion. That is a massive, undeniable economic engine driven purely by our global demand for hydrocarbons. But of course, that staggering economic value has to be objectively weighed against a harsh environmental reality. Over 70% of human-caused greenhouse gas emissions come directly from combusting these exact fossil fuels. Burning these saturated and unsaturated hydrocarbons inherently releases carbon dioxide, and that accelerates climate change and causes severe ocean acidification. Now, when regulating specific fuels, a key contrast to consider is the differing impacts of coal versus liquefied petroleum gas, or LPG. Coal gas is made through the destructive distillation of coal. Burning it generates massive amounts of particulate matter, smog, acid rain, and get this, it even releases naturally occurring radioactive materials like uranium and thorium into the atmosphere. LPG, on the other hand, which comes from petroleum or natural gas, provides a significantly cleaner domestic burn. It's just a vastly less polluting option for things like household heating and cooking. And this leads us straight to the real human cost of energy policy. Look at these death rates from accidents and air pollution per terawatt hour of energy generated. Coal results in nearly 25 deaths per terawatt hour. Oil sits at over 18 deaths. But natural gas, even though it's still a hydrocarbon, it drops that number drastically to less than 3 deaths per terawatt hour. The specific type of hydrocarbon we choose to utilize completely changes the public health outcome. To put a final, really sobering number on this, global air pollution specifically tied to fossil fuel particulates was responsible for over 8 million premature deaths in a single year. That's practically 1 in 5 deaths worldwide. When we talk about evaluating the true cost of fossil fuel reliance, this data is absolutely critical. Which brings us to our final segment, Section 5, Future Energy, Methane Hydrates. Let's conclude by looking at the high-risk, high-reward frontier of future extraction. Look beyond the conventional oil wells and coal mines we're used to. Enter methane clathrates, or methane hydrates. These are essentially massive deposits of methane gas trapped right inside crystal structures of ice. We find them deep down on the ocean floor and locked away in terrestrial permafrost. And they represent an absolutely massive, currently untapped reserve of energy. But going after them, that represents what scientists call the clathrate gamble. The energy potential is staggering for sure, but the risks are right up there with it. Harvesting them runs the immediate risk of destabilizing the seafloor. And long term, if ocean or permafrost temperatures rise even a little bit, it could trigger the clathrate gun hypothesis. That is a disastrous scenario where an abrupt chain reaction of methane release rapidly spikes global temperatures. Some scientists actually believe a similar event caused a mass extinction 251 million years ago. No pressure, right? So as you go back to shaping our future energy grids, I want to leave you with this final provocative thought. Will the harvesting of methane clathrates be our next great energy source? Will we master this new hydrocarbon frontier safely? Or will it master us and act as the trigger for a disastrous climate chain reaction? Thanks for joining me for this explainer. I hope this look at the microchemistry and the macro impacts helps you make informed, data-driven decisions moving forward. Keep learning, and I'll see you next time.